In this tutorial, we'll be learning how to do multivariate analysis. Both of the analyses for crosstabs and regression are really just extensions of the techniques that you use for the bivariate analyses, only you're adding extra variables. It's a little more complicated for crosstabs, but regression is really a much simpler extension of regular regression. Let's first take a look at multivariate crosstabs. We'll use the GSS 2000 data set here. And we're going to be looking to explain a particular variable called gun law. And what gun law is a measure of the respondent's opinions about whether guns should be required to, a permit should be required for guns. Go down here and look at it. Takes on two cases here, favor or oppose. 0, 8, 9 are missing values, so it's just a simple binary variable. And we're going to use two different variables to explain this public opinion on gun laws or gun permits. First of all, we're going to look at whether people have guns themselves, whether they own guns, with the expectation that gun owners are going to be more likely to oppose gun permits and less likely to favor them. And we're going to look at partisanship. We have a 4-category party identification variable with the hypothesis that Republicans are going to be more likely than Democrats or Republicans to favor the Democrats are going to be more likely to favor permits, Republicans are going to be less likely to favor permits, and independents and probably going to be somewhere in the middle. Okay, so what we can do is go up to our descriptive statistics, go down to crosstabs where we normally get our crosstab menu, resort our variables here. Okay, and then as usual we'll put our dependent variable in the rows because columns cause rows. So we'll find gun law here. Place that there. Then our first independent variable is going to be whether a person owns a gun, and that variable is called own gun. Okay, and that goes in the column setting. Now here's where things get a little different. For our second independent variable, we're going to place that down here in the layers box, layer 1 of 1. And the variable we're going to use is called party ID 2. It's right there. And we'll place it down in the lower box. Okay, so you have your dependent variable, you have your first independent variable, and you have your second independent variable. Now it matters to some degree whether you place which independent variable goes into which box, because really down here this box is going to be considered your control variable, whereas this is going to be considered the variable of interest. And you can look at the relationship between both, both ways, but your measures of association are going to be calculated based on which is your control variable and which is your variable of interest. And I'll show you what I mean by that in a minute. First of all, we have to go back and ask for our column percentages so we can interpret our tables. And we'll want to ask for our measures of association. And in this case, we'll ask for Kramer's V, and we'll ask for lambda. Okay, we go to our output here. All right, you can see this creates a pretty big table, but we have over here basically a crosstab between gun ownership, which is our independent variable, and our dependent variable here is whether you favor or oppose gun permits. And then we have our control variable categories, Democrat, Independent, Republican, and other party, and then this basic crosstab is reproduced within each of those categories. Now note that within each of these crosstabs, there's sort of sub-crosstabs, that the columns all sub to 100. So this subs to 100, or totals to 100, this totals to 100, and so does that. And then within this crosstab here, we have a total to 100 and a total of 100. So we still have our column percentages summing up to 100% within the crosstabs for each of the separate control variable categories. Now if we look at our relationships here, just to interpret this crosstab, we can see a difference here between gun owners. Those who own a gun are much less likely to favor permits, right? 90.5 versus 78.9. And that difference is true among Democrats, it's true among independents, true among Republicans, and it's even true among other party supporters. So it looks like gun ownership is has an influence on opinion about gun permits, regardless of or controlling for party identification. Now, again, it's useful to go down and look at those measures of association. Here, as it turns out, lambda doesn't produce anything because of the way that the table is set up, so we have to go turn to Kramer's V down here. And we can look at the Kramer's V for the Democrats, 157, for Independents, 225, Republicans, 288, and for the other party supporters, 196. So you can see there's a moderate relationship between gun ownership and public opinion on permits in each of the categories, which suggests that we have a real relationship here between those two variables. Now, I wanted to point out that you can look at the relationship of party identification on public opinion controlling for gun ownership. So you can sort of reverse the control variables. But the comparison's not easy to do in a table like this, because what you're basically going to be comparing is the Democrats who own guns and what percentage favor versus independents who own guns and what percentage favor, and Republicans who own guns and favor. And you can see the pattern here. That is, Republicans who own guns are much less likely to support gun permits than Democrats are. Right? So it looks like party identification has its own effect, even controlling for gun ownership. But we can look at these patterns this way in the table. They're kind of hard to see rather than the normal way of just going across. Plus, we can't get measures of association, because the measures of association are created within each category here. We need to create them for each category of the other variable. So the way to do that is to rerun the crosstab. So if you want to look both ways, you take this variable, move it down to the bottom, you take the other one, and you move it up to the top. So you just reverse them, and then you run it again. Now you'll see here across, now it's much easier to interpret what we were looking down at that column for, 78.9 versus 71.3 versus 61.6. Right, that's the same information we got here. 78.9, 71.3, 61.6, but it's organized in a way that's a little easier to read. Oops. Right, across like that. And then in addition to that, we have our measures of association that are done within the categories of what we're now calling the control variable, which is gun ownership. So this shows you the effect of partisanship on gun permit support, controlling for gun ownership. And you can see that there is an effect of partisanship, 174 for the yeses, for those who own a gun, 0.094 for those who don't own a gun, and then it's actually a relatively strong relationship, 0.210 for those who refuse to even answer the question, although there's only 21 cases that fall there. Okay, so you can do your crosstab both ways, and whether you need to do that or not depends on whether you have a variable that you're really interested in and you just need to control for something else, or whether you're really looking to build a causal model, and so you want to see whether all the variables that you're including have an effect controlling for the other ones. Now, of course, the easier way to do these kinds of causal models is to use multivariate regression. And so what I'd like to show you is how to do that now. And for that, we're going to look at the countries data set. And what we're going to be interested in explaining is economic inequality. And there's a variable in this data set called rich 10, which is the richest 10% share of income or consumption. Right? So if you had perfectly equal distribution of wealth, the richest 10% would have 10% of the income. If you had really high levels of inequality, for instance, the richest 10% might have 90% of the income, and the remaining 90% of the people would get the remaining 10% of the income. So the bigger this number is, the more inequality you have. And so that serves as a decent index of how much inequality, economic inequality there is in a country. And we're going to try to explain this inequality with two variables. One is voter turnout. So we might hypothesize that when there's higher turnout levels, the people the masses who tend to be the middle class and lower class individuals are going to demand laws that are more redistributive, that prevent the rich from maintaining a very high level of inequality. So in other words, the democratic masses will try to equalize the economic distribution of wealth. And then we'll also hypothesize that the literacy rate has an impact on it. By suggesting that a more educated population is more likely to be able to find better jobs and compete for those jobs, and so you'll have a broader distribution of wealth more of a well, educated middle class. And then finally, we're going to hypothesize that newspaper readership or circulation has an impact on economic inequality on the grounds that a more informed population is going to demand laws that are more equitable in terms of economics. Okay, so 3 hypotheses. Now, how would we test those? We'll go down to regression, ask again for linear regression. As usual, we'll sort our variables. Okay, we'll put our dependent variable in here, which is that one I showed you, rich 10. Okay, and then we just stick all of our independent variables in the independent box. Pretty simple. A lot easier than the crosstabs. They all go in together. So we have voter turnout, which is VAP. We have the literacy rate here. And then we have the newspapers circulation. Okay, that goes in there, and that's all we need to do. Hit OK. Okay. All right, so here's our output. It's going to show you again, all the variables that were entered. You have a model summary where you have your R² here is 0.230. Right, so this provides a sense of how well the variables as a set explain the dependent variable. They explain about 23% of the variation, or another way to talk about it is to say that 23% of the errors in explanation are reduced with the independent variables in the model. So it does a pretty decent job. We'll skip over the ANOVA box until we talk about statistical significance, and we'll go down to the coefficients here. Now you can see here that it looks just like the bivariate regression box in terms of what the columns are, but you just have more rows. You have the constant, that's our y-intercept, but then you have a regression coefficient for each of the independent variables in the model. Now you have your unstandardized coefficients, which tell you the change in y associated with a unit change in x. And then you also have your beta coefficients here, which are standardized and allow for comparisons across variables with different metrics. Now, just to do a quick interpretation of this output, we see here that as voter turnout goes up, inequality goes down. So that's the hypothesized relationship. Literacy, on the other hand, does not seem to have any impact. It's a very, very small coefficient. The beta coefficient is very, very small, so it suggests that literacy rates do not have much impact on inequality. Newspaper circulation, on the other hand, seems to have a very strong effect. The greater the newspaper circulation, the lower the level of inequality. So that seems to pan out. And in fact, if we look at our beta coefficients, newspaper circulation is the strongest variable in the model. It beats out voter turnout here by just a little bit, 368 versus 232. Now the last thing I wanted to show you with regression is how to create dummy variables, because sometimes you have an independent variable that's nominal or ordinal, and you can't just stick it into the regression equation. For instance, in this data set, we might be interested in looking at the effects of how free a society is, on the grounds that a society that's more free will have greater opportunities for people to advance themselves, and therefore there'll be a more equitable distribution of wealth. Well, there's a variable in the data set that will allow us to do that. It's called the freedom status. And the problem is that it takes on these 3 categories. They're ordinal, right? So they go from the least free to sort of partly free to the most free. But they're not interval level. That is, the difference between 1 and 2 isn't the same as 2 to 3. So you can't just stick this in a regression model and get an outcome, because the unit change in x, 1 to 2, 2 to 3, doesn't mean anything, right? But what we can do is create dummy variables for these 3 categories and then introduce those dummy variables into the regression model. All right, how do we do that? Well, what we need to do is come up to transform, and we're going to recode variables, recode into different variables. And we've already looked at how to do this. But the key to doing this is to create 3 new variables, one for each category of your original variable. All right, so let's go down and find free stat here. Okay. Now we're going to recode. The first category is going to be free. We're going to call it free. Oops, let's not make it capital. All right, we're going to change the label there. The old and new values. Okay, so now the old code was for free was 1. So anything that's a 1 is going to be entered in as a 1. All right, seems pretty simple. And then all other values are going to be coded as 0. So we hit continue, hit OK. All right, now if you look at your data view, we can just make sure that that happened. We can go down, we can see the dummy variable here for free, so it looks like it recoded that. Now let's go back and do that again. And then we're going to call this one part free. Make that change. All right. So anything that, we can actually just do this. Anything that had been a 2, because that was the partly free code, is now going to be a 1, because it's going to be indicated as a dummy variable with a 1. And then everything else that's not a 2 in the original coding scheme, that is countries that were free or not free, are going to be coded then as a 0. And everything that was partly free, which is a 2, is going to get coded as a 1. Okay. So that works. And then we can go back here and do it again for our not free category. Click change, old and new values. Now we're looking for the cases that had been a 3 in the old variable are now going to become a 1. Hit change. So 3 not frees become 1 in this new dummy, and everything else stays 0 or becomes a 0. Okay, so now we've got our 3 dummy variables for countries that are free, partly free, and not free. And it's worthwhile to come through and just make a check that everything's working out. So that each one has a code of 1, and none of them have more than one code of 1. And it looks like the recoding went through successfully here. Okay, so now we're going to introduce these into our regression equation, but we've got to leave one out as a baseline. And I'm going to suggest that we leave out the not free category, the third one. We could do it a different way, but that makes sense because this will then tell us what the difference is between part free and not free and not free. Now we can go back to our regression that we just ran here with our 3 variables and enter these new variables into them. So our first dummy variable is going to be called free. So add that in. And our second one is part free. There. And then we're going to leave not free out. That's going to be the baseline. We'll hit OK here. Take a look at our output. All right, we can see our R squared does go up a bit. It had been 0.23, I believe. We can go up and look. Yeah, 0.23. So adding in those 2 dummy variables now boosted up 0.3 to 0.320. So it adds another 10% explanatory power to the model. Then we can go down and look at our coefficients. We can see that voter turnout still maintains about the same effect. The literacy rate is still very minimal in terms of its impact. Newspaper circulation retains its strong impact, especially looking at the betas. And then if we go and we look at our 2 dummy variables, we can do some comparisons here, right? So if we look at this, we find some interesting things. For one, our hypothesis doesn't pan out exactly. It pans out to some extent in the extent to which, well, let's see. Let's interpret this right. The richest 10% share, that's our dependent variable. That's income inequality. It's higher in free countries than not free countries. Okay, and it's even higher than both free and not free countries in part free countries, where it's 6.9 percentage points higher. So this suggests that the countries that have the least income inequality, that are most equal, are those that are least free. So our hypothesis is turned on its head, but it's not a linear or monotonic relationship. In other words, it doesn't go not free, part free, free in terms of inequality. Instead, the lowest level of inequality is found in not free. The second highest level of inequality is found in free, and the highest level of inequality is found among the partly free countries. So an interesting result. Now, you'll note too that by creating these different dummy variables, free, partly free, and our excluded category, which is what these are compared to, allows us to find this nonlinear relationship, which we might not otherwise have noted if we had tried to just stick this variable in as an ordinal level variable and cheated the rules. So it's helpful in this regard to be able to do that and create these dummy variables, and allows us to look at the impact of an ordinal level variable like this within the context of a regression equation.